Hi there, folks. Today we're looking at scientific notation. And yes, I am aware that this is a math class and I am a math teacher, but scientific notation goes hand in hand with some of the rules of exponents that we've been talking about, all right? So scientific notation is this shorthand way, it's an abbreviation for really large or really small numbers, okay? And we basically express them in terms of powers of 10. So we're going to use our rules of exponents to kind of express really big and really small numbers, all right? Scientific notation is always in the form a times 10 to the n, where n is some integer, positive or negative, and a has to be greater than or equal to 1, but it has to be less than 10. So it has to be a single digit number with decimals, all right, is essentially what it comes down to, all right? It cannot be like 0.5, all right? It has to at least hit that 1 mark, and it can't be 10.1, all right? It has to be under that 10 value, so 9 point something would be okay, all right? So we always want a single digit number with decimals if we need them, and then 10 raised to some power, okay? For example, if I look at these are all scientific notation. Notice 8.3 times 10 to the fifth, all right? That 8.3 is a single digit value with a decimal tacked on, all right? And then 10 raised to the fifth power. It can't be raised to the 0.5 power or 2.5 power, something like that. It has to be an integer. The next one, 4.12. See that 4.12? It falls between 1 and 10. It's a single digit with decimals times 10 to the 22nd. And then the 7.1, also the 7.1 between the 1 and the 10, it's a single digit with decimals, and then 10 to the negative fifth. And yes, negative exponents are okay here, and we know how to deal with negative exponents. Remember, that's a fancy way of writing division. For example, it says state whether each is in scientific notation. So again, does it follow the rules? So here, 0.23 times 10 to the negative third, that does not follow the rules of scientific notation because this first value is not between 1 and 10, all right? So the answer here would be a no, that one's not in scientific notation, that's not okay. And at some point here, we'll look at how to rewrite that in scientific notation. If I look at the next one, very similar, but instead of a 0.23, it's 2.3. So now the 2.3, that falls within that acceptable range between 1 and 10. And then I have times 10 to the 7th power. Well, that looks great. So yes, this one is scientific notation. All right. And then if I look at this third one, it says 9.3. Well, that's good. That's between the 1 and the 10. So that is perfectly acceptable for the 9.3. But then it says times 100 to the 9th power. And remember, in scientific notation, it has to be times 10 raised to a power. It's powers of 10 that we use to express this. So this one is not in scientific notation. And it's important to recognize because, again, when you're dealing with things in scientific notation, you always want your answers to be in scientific notation. And sometimes we'll get answers that pop out in things that are not scientific notation. We have to then fix them, okay? And that's what we're going to learn to fix those at some point here. So rewrite each in standard form. Standard form is like when we write the number the way we would normally write it, all right? We write that really big number with all the commas and that kind of stuff, all right? So 5.5 times 10 to the 6th power. If we just think about exponents here, we know that if I literally did 10 to the 6th power, it would look like this. It would be this number, 1 billion, okay? So really what this says is 5.5 times 1 billion, so that's going to give me this. It's going to give me 5.5 billion, all right? And if you've done this in science class or anywhere else before, you know that you don't actually have to write that out. There's a little bit of a shortcut here. If you start thinking about what happened here in terms of doing the shortcut, you can just take that 5.5 and you move the decimal 6 places to the right, okay? So we move the decimal to the right 6 places. That's our shortcut for scientific notation, okay? And the reason that works is because this is essentially just multiplying by exponents, okay? If I look at the next one you might know the shortcut for, but let's think about it from the perspective of actually using the exponent. This is 3.1 times 10 to the negative third. Well, remember, negative exponents mean I actually want to divide by that 10 to the third. So really what this is saying is 3.1 divided by 10 to the third. And again, 10 to the third power is 1,000. And if I actually divided those things, you could grab a calculator and do it. It would be 0.0031, all right? And again, the shortcut here, if we think about it in terms of a shortcut, is we just, when we have the negative exponent, we move the decimal that many places, but to the left this time, okay? And so again, most of us probably know the shortcuts for these, but did you understand why you're moving it to the left when you have a negative exponent? It's because you're doing division, all right? And hopefully understanding what a negative exponent really is, that it just means division, it would make sense that the exponent moves to the left, or the decimal moves to the left, okay? When we multiply, like in the example on the left here, the 10 to the 6th power, when we multiply, we get big numbers. But when we divide, we get smaller numbers. And so that's the kind of the general basis for scientific notation. We're using rules of exponents to manipulate the numbers and write them in this shorthand version, okay? Now, I wouldn't expect anybody to write them out every time. I expect us probably to use the shortcut. So here we go. Here's what it looks like when we use the shortcut. I'm just going to write down the 4, 1, 2. And now times 10 to the 12th, I'm going to move it 12 places to the right. So I'm going to scoot that decimal over. It was right here, but I'm going to move it 1, 2. When you run out of spots, just start tacking zeros on. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And each of those spots gets a 0. Oh my. Whew. That is a huge number. And now let me rewrite it. And one of the most common mistakes that students make here is they'll put 12 zeros on the end and forget about moving it past that 1 and the 2, that counts as 2 of the places, okay? So the 4.12, you move it 2 places to get past the 1 and the 2, so then there's only 10 more zeros that you have to tack on, all right? If I look at this one, again, same kind of thing. I'm going to move the decimal the other way this time in 5 units, so 1. But now when I run out of spaces, 2, 3, 4, 5, I use zeros in there, okay? And so this becomes point, and there it is, scientific notation. The reason that's happening, though, is because I'm literally dividing by 10 to the 5th power. That's what scientific notation uses, all right? It's essentially multiplying by 10 to a power or dividing by 10 to a power to either give us a really big or a really small value, okay? If I look at something like this guy, let's write them in scientific notation. So again, think about where you need to put the decimal point in order to get a value that's between 1 and 10. So like if I put the decimal point here, that wouldn't be any good because 1,430 is too big. If I put the decimal point here, that's no good because 14.3 is too big. I have to put the decimal point here. So then essentially my number becomes 1.43. And then it's times 10 to the what? Well, all we have to do is count how many decimals we moved it. So back up here, ready? 1, 2, 3, 4, 5, 6, 7, 8, 9 values. So it's 10 to the 9th. Okay? And again, because it was a really big value, we use a positive exponent to express it. If it's a really small decimal, we'll use a negative exponent to express it. So now this one, think about where you need to put that decimal. I can't put it here because 0.1, that's too small. It has to go behind that 1. And so here's what I get for my value. I get 1 times 10. We'll count how many decimals we had to move that thing. All right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values. And because it was 10 in that particular direction to give us this small decimal, it's a negative 10 for scientific notation. Okay? If I look at something like this guy, again, think about where, whoa, sorry, it jumped on me. Think about where you need to put the decimal. The decimal needs to go here. So that's a 5.14. Count how many spaces you have to move to get there. Looks like 3, 4, 5, 6, 7. So it's times 10 to the 7th. That's it, okay? If I look at the next one, think about where that decimal needs to go. It has to go here to give me the appropriate size value. So that's a 3.2. And then it's times 10 to the what? Well, count how many decimals we had to move to get there. Looks like 5 units, but it's 5 units in a certain direction. It's 5 units to give me a small decimal. So that's going to be a -5. Okay? And you can always check these on the calculator by plugging them back in. Literally do 5.14 times 10 to the 7th and see if it gets you the original problem. Literally do 3.2 times 10 to the -5th and see if it gives you that 0.000032. Okay? But now comparing numbers in scientific notation, if I look at something like this guy, it says the map below shows the surface area of 4 major oceans. List the oceans from least to greatest. Okay? And so here's the thing. When you're thinking about scientific notation, the number out front doesn't matter in terms of the size as much as the exponent that's on the 10. Okay? And see, it's really important to kind of think about that. Like if I had, I could have like the biggest number possible in scientific notation, 9.9 times 10 to the smallest number possible. How about first? And then I could have the smallest number in scientific notation, like 1.0, but have it times 10 to the 5th power, and hopefully understand that the 1.0 times 10 to the 5th power is bigger, because when you start to move the decimal, that first one converts to a 99, whereas this one converts to a 100,000. Okay, and there's a big difference. The exponent determines the size more than the number out front. Okay, now if they had the same number up top here, like if this was a to the 5th power, that means the decimal is going to move the same number of places. Well, now the 9.9 being bigger than the 1.0 is significant, okay? So keep that in mind when we're talking about scientific notation. The size of the exponent determines how big thing is, more so than the number out front. So as I look at these, if I want to list them, let's see, did it say least to greatest? Yes, least to greatest. So as I look around at this thing, there are 2 of them that have a 10 to the 7th power, okay? And 2 of them that have a 10 to the 8th power. So the 10 to the 7th powers, those are going to be smaller, but when they have the same, well, which one of these is bigger? Well, obviously the 1.41 is smaller than the 7.49, so it's 1.41 times 10 to the 7th, followed by the 7.49 times 10 to the 7th, okay? The exponent tells us that those are close to the same size because they have the same number of decimals in terms of that move, but the 1.41 is smaller than the 7.49. And now both of the values with the 10 to the 8th are going to be larger than the 10 to the 7th, but again, we'll go to the number out front to determine their order, 1.06 times 10 to the 8th, and then the 1.8 times 10 to the 8th. And again, those will have the same amount of decimals that will move, but the 1.8 is bigger than the 1.06. So that's how we kind of compare things in scientific notation. And actually, that's easier to compare these than if we were looking at the standard form of the numbers, okay? With the standard form of the numbers, we'd have to kind of look a little bit closer and count up how many values we had. With scientific notation, it's really easy to see, oh, the 8's bigger than the 7, so the things with the 10 to the 8th are bigger than the 10 to the 7th, okay? So again, scientific notation, that number out front has to be a single digit with decimals, all right? We use a positive exponent to express really big numbers, a negative exponent to express really small numbers, all right? And that exponent, the shortcut is, it just tells us how far we need to count to get the decimal in the right spot, okay?